I'm a lead data scientist. I work in deep learning on document images. So let me introduce myself. As I said, I'm a data scientist, and I generally work in an area where it involves a lot of automating things using ML and DL. So I mostly work on document images, tabular data, and chatbots. Even I work on OCR as well. I just want to share my knowledge on how deep learning can be used in document images. So by what I mean is how can we extract content from it intelligently than just simply OCRing the documents and no extracting the text. So I'll be walking you through. Let me take you through the agenda. This is so basically we will be sorry. Okay. Okay. So we will have. So basically, this is generally we will be walking you through some of the history of deep learning in document images in object detection, and what are there are certain two-stage methods. There are single shot methods, and a demo using RetinoNet on document images. So first slide I'll take you through. So the problem definition. So basically in an object detection, the problem would be to identify the object in an image. So given an input image, you will predict the locations of certain class of an object in an image. So location of that object, which is like bounding boxes, is used to calculate the IOU, intersection over union, to identify whether the identified object is accurate or not. So evaluating using, so we will evaluate the object detection using IOU. So this is simple explanation of what a certain metric in object detection. So this is simple one that, and motivation localizing, this is one more thing, like localizing the objects. Say in computer vision problem, this is a big problem. Like even in autonomous driving or with robots, you should localize where the object is, and take actions accordingly. So that's where the localizing objects comes into picture. And before deep learning the before deep learning, the object detection used to be done using hog. Like there are hog, sif, there are various features that people use. Generally hog is something which is very popular, wherein it's in a histogram of oriented gradients, wherein you convert an image into an 8 by 8 pixel. After that 8 by 8 pixel, you will brought that pixel into a nine values, nine boxes, like that, which you see the histogram of gradients. So you will convert the 8 by 8 pixel into 9 values, basically all the 8 by, then you perform SVM using those features. So that's how it used to be done for object detection before deep learning. So these are handmade features that you make. These are handcrafted features, because you're doing it by 8 by 8, and then you are calculating that those 9 values, and taking that feature extraction, doing that feature extraction, and after that you're training a classifier called you train a classifier with those features, extracted features. So this is how it was done before deep learning. Okay. So actually is it's a big object detection model, but this picture represents still object detection models till 2019. Those whichever are highlighted in red are basically which made good impact in the object detection model, like RCNN, overfeed, and fast RCNN, faster RCNN. So there OHEM, YOLO. So these are some of the what do you call a path breakers when it comes to object detection models. So that's why it was highlighted in red. So there are various say for example RFCN and FPN. FPN may not be an object detection model, but it helps in having that the object detection models, like say for example it is used as a backend in RetinaNet. So RetinaNet is one of the popular ones. Mask RCN and one more popular one, YOLO V3, Refined Det, M2 Det, and there is one more recently Efficient Det has come into picture, and YOLO V4 also is in live, which was released in April 2020. So those are those talks about the timeline of the object detection, various object detection models. And I'll go to the next slide. So when it comes to the next slide, basically there are two types of detectors, like it is a two-stage detector and a one-stage detectors. So what do you mean by two-stage and one-stage is, so when you see an image, you should be probably know where the image actually, where an object of our interest is present. So for that, for identifying the object that we need to identify, there's a concept called region of interest pooling. So what it does is it gives you a sample of bounding boxes, like 2k or more than 1k, 2k, like that, which is a list of bounding boxes which tells you where the object would be. So in two-stage detectors, one stage consists of this region of interest pooling, which helps in identifying the objects. Later, the after region of interest pooling, then you will classify. Then you will basically with those regions of interest, you will calculate IOU based on their confidence scores. You will have a classifier and you will have a regressor. So this is something which is like which is the pipeline that happens in a two-stage detector. Whereas in one-stage detector, you will not have that region of interest pooling. You will have many bounding boxes that actually tell you how the object, where the object is. So when it comes to fastness, one stage detectors are more faster because it doesn't have that region of interest pooling layer. When it comes to two stage detectors, they are very accurate because of that region of interest pooling. So these are the say, when if you go for RetinaNet, you will have fastness, which is the reason why I chose RetinaNet for document images is that it is fast and it is accurate also at the same time, because it has 100k bounding boxes which checks where the object is. Along with that, there's a concept called focal loss, which I'll be walking you through in coming slides. Okay, so that's on the type of detectors. So any questions as of now? Nothing. Okay, I'll take that as no. Okay. Okay. So one question. Let's start. Yeah. Okay. So I think, yeah, fine. That's very much when it comes to that's very much when it comes to the type of detectors. And let's go into RCNN. RCNN, as I was saying, it's like you take the input image and you extract reason proposals from it, and then you will pass it to a CNN architecture, which gives you the regions as well as the classification and regression model will give you the bounding boxes result, whereas classification will give you what type of object it has. So basically RCNN is the first model that came into picture for object detection. So this is the simple. I'm just giving a simple walkthrough so as to not waste time on on other object detection model. We will be concentrating more on RetinaNet. Okay, And fast RCNN. Fast RCNN is also the same in a similar fashion, where you have ROI projection, ROI pooling layer that comes into picture with fully connected layers. So this is something which is fast RCNN. This is an improvement on RCNN. Then there's another in the family which is faster RCNN. So this is one more architecture where RPN came into the picture. Here, regional proposal network came into the picture, and it is one of the well performing models even now. So that's faster RCNN for you. And so when we'll go into one stage detectors now. So far you have seen whatever you have seen is, be it RCNN, be it fast RCNN, or be it faster RCNN, you have a region pooling layer here for object detection. But when it comes to one stage detectors, basically, okay. Differences between YOLO and okay, differences between YOLO and RCNN. YOLO is a one-stage detector, where an RCNN is a two-stage detector. So, but YOLO V3 is performing far better than RCNN. So YOLO, I would say YOLO V4 is better than RCNN. But even in terms of performance, YOLO is far better than RCNN. Even in now YOLO V4 accuracy wise, it is far better. So that's one question that came in. Yeah. And another one stage detector. The problem with one stage detectors is that, as I told you, there is no region pooling layer, which means there is no other layer which detects where all the objects of our interest are. So it actually takes a 100K sample. When it comes to RetinaNet, it takes 100K bounding boxes that you could see, like you could see a green, a red, right? So when it comes to green, you could see there are few positive examples, rich information, which means those are the positive samples that you are interested to identify, based because those has objects. So when it comes to many negative examples, no useful signal, which is like red area, so you will have many bounding boxes which doesn't have the object of your interest. That's where the problem with one stage detectors come into picture. So how is that being solved in RetinaNet is what we will see in coming slides. Okay. So any questions on this, on, on the problems in one stage detectors? Nah, great. Okay, I'll walk you through in. So when it comes to number of bounding boxes comparison, so this is a simple comparison as to how many bounding boxes are being used in one stage detection. Okay, so YOLO V1 uses 98 boxes, YOLO V2 uses 1K boxes, SSD there's one more one stage detector which uses 1 to 2K boxes, and RetinaNet uses 100K boxes. So in terms of those boxes, and RetinaNet is far higher, and also it is faster. That is something which we should consider. So that's why people prefer RetinaNet, because of its accuracy. It's more on the accuracy side. Um, uh, it's more on the higher side. RetinaNet 100 code boxes, yeah. So that's and YOLO V4 is having higher accuracy. Okay, so yeah. And when it comes to when it comes to the, so RetinaNet, I was saying the focal loss. How will you consider, how will you remove all these many negative examples, right? So that's where the focal loss comes into picture. Focal loss is something which is used in RetinaNet, which helps you to take out this smaller easy examples, a large number of. So cross entropy, as I think everybody knows what cross entropy is. So you could see for y is equals to 1, it's log of p, otherwise it is log of 1 minus p. So in a simple case, if it is pt, so you are simply writing cross entropy of pt is equals to minus log pt. If it is not negative item, if it is so you will have that's a simpler format that you could see in the left side box. And when it comes to when what happens is there are 100,000 easy examples which you see, easy examples, and there are 100 hard examples. So the last computation will be more from easy examples than the hard examples, okay, because of the higher of the number in easy. So what we need to take care of is how to push the easy examples loss to a lower value and hard examples to a higher value. That's what the focal loss does, okay. So when we see the formula, you will probably take a look at it. So there are two parameters in focal loss. One is alpha parameter, the other one is a gamma parameter, so which you see in the alpha based variant of focal loss. So if you see hyphen alpha t 1 minus pt of gamma log of pt. So what happens is, if you use higher gamma values and if you use higher alpha values, so you will be stressing more on hard misclassified examples rather than small easy examples. So if you have if you have a misclassifier, say for example log of p, if the probability is 0.2 and the 1 minus pt value will increase the loss of it, because it was having it is having a low confidence. So that's where the focal loss is. These two parameters which is attached to cos entropy loss will help you to solve the problem of many negative examples, few positive samples. So those which are hard, which this actually gives you much bigger scene as to what is happening in the focal loss. So those how 1,000 easy samples and 100 hard samples will get covered because of this factorization of alpha and gamma combination. So any questions on focal loss? So because this is something, this is a crux of it. Okay, I'll take that as no, and I'll proceed further. Okay. I'll proceed further. And next one. Okay. So this is basically the architecture when it comes to the RetinaNet. So in RetinaNet, what you will have is you will have a ResNet block which has more of this. That's A. In A you will see a ResNet block which is normal ResNet, and then another FPN which is feature pyramid network. Which what if the feature pyramid network does is it just upsamples the various layers of the ResNet. Thereby you will not lose any information. That's this feature pyramid net is something which brings the accuracy into the RetinaNet, and that upsampling helps for the object detection. And each pyramid network will have separate class and a bounding box, which is like a regression problem and a classification problem. Where if you see the B as feature pyramid and C, which is your class subnet, C class subnet, B D box subnet. So what class subnet does is, class subnet is a classification model, whereas box subnet is a regression model. So those two come into picture, but I'll be walking you through the code as well, so you will know what is happening in. So I'll take you through in the code as well. So let me take you through. Before that, let's finish the other slide that we have. So this is basically the how various values of gamma will affect your focal loss. Basically, so your gamma is equals to 0. If in the case of gamma is equals to 0, the focal loss becomes your cos entropy loss, which is your blue line. So as you can see, if gamma is 5, those ground probability of ground truth, those which have lesser values of probability of ground truth class, they will have higher loss when it come when compared to your blue line, correct? So that's where this comes into picture. This focal loss will have that those numbers in place. So that's where this is come into picture. Okay. So because this is a minus sign, you probably whatever is lesser going to be the higher. Okay. So that's what. Any questions on this before I move on to the code? Okay, I'll take silence as no, and I'll move on to the code piece of it. So basically, this is what I have designed for Pyramid Net. So basically, I'll take you through what all happening. So as everybody knows, the ResNet. So ResNet will have this convolution. I'll not get deeper in ResNet. This is just a simple classification that happens. So ResNet also we are using. There are various backends that we will be using. One is ResNet 18 backend, 34, 50, and I will have options for giving them also in while executing the code. So ResNet 152, ResNet 101, all these different architectures that we are using as a backend for when it comes to ResNet. ResNet is something. This is ResNet, and let me show you how future pyramid network is. Pyramid features is basically uh, pyramid features is basically okay. Let me. Yeah, basically yes. High focal loss means lower accuracy. Yes, 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 yes. Let me share my code. I'm sharing my code. Okay. Okay. So everybody can able to see my screen, right? This is I generally use Visual Studio Code for developing models, and I also have when we are executing. I also have a two GPU system at my home, so I built it for myself so that I can research on various deep learning stuff. That is, you know every day it's a new model coming to the market. So it's important to be in up to date to the market. So that's something which I probably did. So I'll probably take you through ResNet, which so as I was saying, ResNet is just give me a minute. Just give me a minute. Sorry for the disturbance. Sorry for the disturbance. I'll so there's this is the ResNet block. I'll not take you. I'll not be walking through the ResNet block because everybody knows what ResNet block has. Those which actually helps in vanishing gradient. All those things we will not be taking through, but we will be looking at something which is specific to object detection model. That is your feature pyramid features, which is your FPN, as I was saying in the diagram that we saw earlier. So in feature pyramid network, what happens is, see, so this C3, C4, and C5 are the layers that we saw in ResNet. Those ResNet blocks are given to the pyramid features, which you could see C5, P5, C5, which means C5 block. in ResNet. So what happens is when we are calling this, correct? When we are creating this C5 and so what happens is when we are using ResNet, sorry, if you see this, correct? So in FPN, we will be calling X1, X2, X3. We will be pushing this to different features, and this X1, X2, these layers, right? Which you see here that are being put in self.fpn, which is your if you see your self.fpn, which is your pyramid features, features which are extracted from your your layers of ResNet that are being passed to the feature pyramid network. So in feature pyramid network, what is happening is you are actually upsampling them. You are upsampling them with different convolutions that you could see. You are taking a C4 side, you are taking a C3, C4 and C5, you are building on top of it, and it's a pyramid structure that comes in. So that's when it comes into picture, and this is some simple forward pass that comes into picture. Okay, then so let me do something. I'll just again show this slide so that everybody will get to know what I'm doing, right? Okay. Sorry. So till now, what we spoke is the till now what we spoke was the first part of it. First part of it, wherein you have a ResNet structure, you have the pyramid, feature pyramid net, right? So you saw C4 is attached to C5, P4, P5, C4 is attached to P4, C3 attached to the P3. So which is kind of A and B section in the diagram that you see in the PPT. That's what I've shown in the in the code that I have shared earlier. So in the after this I'll be showing the class subnet and box subnet. Basically, they both are class subnet is a classification model, and box subnet is a regression model. Let us see how it is being done in code. Okay. Okay. So this is the regression model that which you could see, correct? So and this is the regression, this simple convolution stack of convolution neural networks and the activation functions. So problem and more importantly, I'm a big fan of PyTorch, and I generally use PyTorch more for my research. And this is the classification network. So this is simple normal classification stuff, and where we are calling it is something which is more important, right? So I'll show you where it is being called. This classification regression, you could see this is what we defined before in this class. So that's what come into picture, and you could see what is happening here. So you are actually stacking them, and concatenating them, and using them as features here, and your focal loss. And also let us see what focal loss does, where is it defined. Let us go in focal loss also. So this is the focal loss that I was talking about. So focal loss have two parameters, alpha and gamma. Okay, and this alpha and gamma is something, now I have hard coded it. As you see, I have given those numbers here. But when I share the code with the larger group, I'll make sure that this is changeable as per your requirement. So I'll be giving, when we are giving arguments for training and all, I'll have a good documentation. Currently, this is not properly beautified it. Probably in another 4 or 5 days of time, I'll beautify this and share it with the larger group through a GitHub repo, which I'll share with Vishal. Will probably share with the larger group. Okay. And so if you see alpha, gamma, and this anchor width and anchor sizes is something which is anchors of 1:1, 1:2, and 2:1. Those are the anchors which are 9 in number that comes into anchors. Those are the anchors that are used. 9 anchors are used, and if you could see what is the IO here, also IO calculations, and IO is something which is very important here, and it should be greater than 0.4. So that's what it says. That's what the value that IO threshold is 0.5 that we will be using, and here you could see 0.5. Okay, so whichever greater than or equal to 0.5, that's only those are the ones which will be used. So this is the value that we will be using. I have used basically in building the model. Okay, so this is something which you could probably see when I share the code. Okay, so this is particularly related to the fields related to the code. So any questions on this before I move on to the work that I was doing? Okay, I assume that there are no questions. Okay, so basically, let me show you some other stuff, which is like which is the images probably. Mm, okay, so there are 3 use cases that I was working on. Uh, there was 3 use cases that I was working on. So those 3 use cases, I'll share what are those 3 use cases are. So you could see a image. 1 minute, I think it is loading. So I probably think that you are now able to see a screen, right? Wherein you have an image. So at the bottom of it, you have signatures. So generally, it is little difficult to identify. So how can we use RetinaNet to identify those signatures? Something which I've been working on, and this is actually an industry use case wherein you have many documents and you have to uh, Okay, so then one more question that came in: why are the classification and regression losses computed separately? Okay, so why are they computed separately? Because they are computed separately, but they are part of one loss. The reason being that's actually an object detection has 2 problems. One is identifying where the object is, and and knowing what object is. Your classification model will tell you what object is it, whereas your regression model will tell you where the object is. So those two are separate when it comes to problem per se. So they are and ideally they are computed differently, because the way they function is also different, correct? When you're using classification, you generally prefer to use cross entropy loss, correct? When you're regression, you will use R square loss. So they are basically different problems. So that's why we use different loss computations. But the loss will be, both combined loss will be given to the model while you're fine tuning. Both of them combinedly will help in training the model. They are computed separately, but while this weight updation and all, they are computed as a whole unit. Okay, hope I have answered the question. So, and this is one more, the image I was showing. You will have signatures, and you have to identify where the signature is, and you should check whether the signature is present or not. So this is an ideal industry use case wherein you have bunch of documents and you need to identify where the signature is. So that's when the problem came into picture. This is one problem that I've worked on. There's another problem. Let me share my screen. Let me show you what problem is it. Basically, these are basically industry problems. Okay. Uh, Okay. So so you could see one more. I think it is coming up. So you could see another image, right, in your screens. So this is one more W2 pay stub that is it's an open source data set that I've come across. And if you want to extract information from it, how do you do it? So you have to know where each location is. So for that, need to identify. I've used RetinaNet. That's one way of doing it. So I've used RetinaNet. Basically, I have only concentrated on top three values, which we will see in coming while I'm demoing the. And this has some problem also while identifying. It was not identifying certain portion. I think that is because my data set has a blank portion of it. So I'll walk you through that also. So this is one more use case. Okay, let me show you another use case that I will be presenting it to you in today's demo. Okay, please ask questions if you have any. I would be very happy to answer. Just give me a minute. Sorry. Just give me a minute. I'm actually seeing the examples. So another use case that I'm working on is if you have documents and you have many tables in those images, and more importantly, whatever I'm showing in the slides, all of them are document images. Wherever you saw something, all of them are document images. So just to so there are various data sets that I've used. One is so one more question that came in is the which data set is this? So there are so one is data set of IRS 1040s. That one data set which is available openly, and there is another W2 data set which is available in Kaggle. Okay, and then there is one more Marymount data set which currently you are seeing Marymount dataset. Okay, we will be walking you through. Okay, Marymount dataset. Let's me. Okay, please explain the process of extraction. So I'll be walking you through the extraction. The extraction is not important here. Basically, what happens is in extraction, you identifying where you want to extract. Say, for example, if you see this image that I currently sharing, you see a table here, right? You will have many tables in your document images that you actually have. So you want to extract information from those tables, right? So what happens is identifying table is a big problem. See, extracting content from it is extracting comment from it is easier, correct? Because you can use Tesseract OCR, PyTesseract. You can use and directly extract the OCR. Extracting will be easier, but the problem is identifying where the table is something which is problematic. So that's what we will going to solve with using the RedNet. Yes, we will. We can use PyTesseract and extract from it. The only portion that I'm going to show now is only the identifying portion of it. But after you identify it, based on using bounding boxes, you can extract the information easily. Okay, so that's what that's an easy. You can just pick up a tutorial in any of the Google sites. You will get that extraction information. But what you need to know is where that portion of the bounding box is. That's more important problem that we're going to solve. So I'm going to show what are all the problem that I've solved, and this is actually see table extraction. I'll run the model and I'll show you. You will be amazed to see how well the model is performing. Correct. Let me show you my. Okay. So this is my setup. One minute. I think it is getting shared now. Okay, I think everybody able to see my screen. So I have two GPUs. Both of them are RTX 2080 Ti, which is not, which is actually very cool to have. to do what to do the kind of research that you want to do. Okay, so which helps you to solve most of the problem. I mean, which it's your interest, right? You can, if you have good GPUs in hand, you can play around with many data sets, many problems, correct? So is there a good solution to get data from table? Yes, there is. There is. I'll be probably sharing the code as well for that good data from a table. Yes. Yes. There's a good solution because I'm going to show you some of the stuff, but not everything. Okay, but I'll be in code. I'll be sharing everything. Probably from extraction per se also you will have something when I share the code. But today we will be only concentrating on identifying the information because that is the biggest problem. Okay, to the question that Vishal has pinged me. Okay, and one more thing, controller. Okay, so basically I have trained models for all the three use cases that I have shown earlier, right? One is the signature identification, the other one is your what do you call, the information extraction from W2s. The other one is the table extraction from the Marmot data set. So first I'll be taking you through the signature model. So okay, now I'm running the signature model. Okay, you could see CD CUDA available true. So there is another pop-up that came in. So I'll stop sharing. I'll be sharing that pop-up that came in. Okay. So what it did, now I think everybody is able to see my screen. Yes. So if you see, when I started inferencing the model has identified. I have given an image to the model with the command, through the command line, through a folder. I'm giving the image. You can see how it is identifying the signature. Correct. You can easily say the model is working properly, and I'll have many more images that actually does this. Correct. Correct. Can you see other images that came in? Correct. You could see there are many images. Correct. If you see, it is detecting very accurately wherever the signature is. It is, and even if you see the bounding box of the length, it is increasing to a maximum. Correct. Wherever the signature, you can see the length of the signature it is getting extracted from. Correct. There are around 20-25 examples that I have worked on. I mean, not I actually I have trained the data set with more than 400 examples. Okay, so that's why the accuracy is very higher. You could see how it is detecting the signature, and the length of the bounding box accordingly changing as per the signature identification. Okay, this is something very important. Okay, this is actually a good use case because there are problems wherein you will have problems in identifying a signature in a document. You can probably solve this problem using this RedNet, and this is a big problem in most of the banks or financial institutions or on tax companies. Just give me 1 minute. So that's one use case. Let me show you the another use case. Okay, this is some logs that, 1 minute, I think it is getting shared. Sorry. Yeah, I think you could see it's just that it is you could see the time that it is getting detected in the logs that you could see in screen. See, it is detecting in 0.9 seconds, 0.10 second. So this is actually it's a beautifully model which can be used in production. Correct. So if it is that faster, people can easily adopt for a what do you call your production level performance that it is giving us. Okay, so now again I'll walk you through another example where we can identify a text in We can identify a text in W2 forms. W2 is basically like a payslip in US. So those W2s, let me, as you see my screen, I've actually trained a written on it, that PT file that I'm just giving it to val annotation CSV, which has paths for images. Okay, so just to give you, and I'll be sharing this code as well, wherein let me share the result screen that is coming up. So I think it is. I think everybody is able to see now. So as you see the screen, I have trained only those portions where you could see the red line. So you could see for address and the wages. Only I have trained for those two, for three locations basically. But the other, is it location invariant? Yes, yes. There was a question that came into picture. Location invariant? Yes, yes. That's why we train the object detection model. So that's where the object detection. Otherwise, if it is not location invariant, right? What happens is you can simply use an OpenCV to detect it. As the model has to be location invariant, we will use object detection models. Okay, to answer that question that is saying location invariant. Yes, yes, it is location invariant. Yes, yes. And this is one more result that I have, one more model that I've trained for identifying only just employee address and wages, as you could see. Okay, let me walk you through another few more examples. Like if even if it is tilted, it is identifying, but OCR fails in tilted documents. Okay, so just to give you another info. Okay, and once you identify those boxes, right, it is easier to extract the information. Once you get that bounding box, you can just pass it to an OCR by Tesseract, as I was saying earlier. It extracts the content beautifully, or you can use any licensed software like Abby OCR. Okay, this is one like it is if you would see it is working beautifully fine. It's extracting properly all the images and all the text, so you could see the problem being identified, problem being solved accurately, correct? So that's where things come into picture. So you could see, I'm just fasting it up because we don't have time. There's another thing that I have to showcase. So that's comes to, so another this is, and one more thing, and these two problems are aside, another table problem is aside, because when you see table problems, right, the table can be anywhere in the image. So what I felt was table was something with table identification, which I'm going to show now, is a far bigger problem than the other problems that you have seen. Identifying signature or identifying your amount values and all is little easier when compared to the table identification. Let me walk you through that also. Okay, sorry. Okay, and you could see the result that is getting up, the error logs for the log. Not so you can see my screen, right? So you can see the logs that are getting. It is very faster. I mean, you could see two elements that are being identified in 10 seconds. It is not 10 seconds, 0.10 second. It is production level performance. Believe me. Okay, let me sorry, clear the screen before I input something. Okay, so now we are going to perform on Marymount dataset, which you could see. I'm just visualizing the dataset CSV, this validation dataset, valid annotation CSV, and the table models.csv. This is the retinal that I've trained. Let us see how it is performing. Okay, stop sharing. Let me stop sharing, and let me show you the model that I've trained. This is actually a complex problem, and this is actually very helpful in industry use cases as well, where you have any use case on solving the on solving extracting content from the tables in images, not in PDFs. Okay. PDFs, you have many libraries. So you could see in the previous example there was no table, but in this document you could see a table and it is extracting properly fine. And you will see in coming examples, in coming things, you will actually see tables of varying sizes being detected properly. Okay, you could see this there are three tables in this page and it is able to detect properly, as you could see, correct. uh, and this doesn't have it and it didn't detect it. Here it is, you can see it is being properly detected, and and sometimes the object detection model will have problem with the edges of it. You could see some of the content being cut, but while you are extracting, you will have that 5 pixel adjustment that you do while extraction. So that is handleable, that can be handled. I mean, if people have questions on whether while extraction will we be having any problems, no, because you will have that width, you will take care of that width adjustments while extracting. Okay, just to give you some info. So here also you could see the tables, there are two tables and they are being detected properly, correct. And this doesn't have any table, so it didn't detect anything. Here also in this image also you could see there's nothing in the image, it didn't detect. Here you could see a table and it detected properly. Okay, so that's how the accuracy is. I mean, you could see many varying sizes of the tables that are being detected in previous examples that you saw, correct. This is the Liger one. If you see this is smaller table, but still it is being detected, correct. That is something even I was astonished on the performance of the model that I've created. If you So these all the pages that doesn't have a table, so it didn't detect anything. That's a good scenario, right? It doesn't have any false positives, correct. So if you, even in this case, it is the same case. Even here you have a bigger table with, so far I think this is the bigger table, but still it is being detected, correct. That's a great performance that that RetinaNet is giving. Here also this is the same case. Here also, and to some question location invariant, you could see this is location invariant. This is called location invariance, correct. To the previous question that was asked, correct. Okay, so that is from my end. And okay, any questions? I mean, this is from any Q&A. I think we have 3 minutes still. If anybody has any Q&A question answers, I will be very happy to answer. I would take that as no. Okay, do you have to provide the tables of different sizes in your dataset? Do you think that plays a part in it, or retina is capable of handling it on its own pyramid? No, while training, yes, you have to give. I've used there's a VIA annotator tool that I've used. You have to give annotations while training, while after you train it, that's like any object detection model. Okay, if I understand, this is valid for images but not for PDF. Yes, yes, yes. Even in the PDFs, you can convert those PDFs into images. Even if you can, if, there are you can convert that PDF into image, then you detect the table, and PDF can be converted into a searchable PDF and from that PDF itself you can extract based on the bounding boxes, using bounding boxes that is detected by the RetinaNet, that is given by the RetinaNet actually gives you the bounding boxes and the type of the content that is being recognized. Yes. Do we need to train our own OCR for recognizing signatures? No, we don't need to train your own OCR for recognizing signatures. So RetinaNet is capable of doing it, which you have seen. So that is not an OCR. So you don't need an OCR for recognizing signatures. You just with simple recognition model, simple RetinaNet will solve your problem. Okay. So just to answer that OCR question. Any other questions? Okay. I'll keep. Still, we have 1 more minute. If anybody has any other questions, I'll be very happy to share. I'll be very happy to answer your questions. Okay, can we not use PDF? Do we need to? Yes. We need to use images only because uh, that's how the object detection models works. So the input has to be, but that's easily solvable problem. That's not a problem. Yeah. Thanks for the nice. Thanks Vishal. Thanks everybody for attending the presentation. I'll be sharing the code in 1 week's time. Probably next week. By next week, you will have everything. The code, the everything. Yeah. Thank you. Thanks for everybody. Thanks Vishal for the coordination. Thank you Vishal. Okay. Will Retina solve all the image problems? I mean to say, what is image problem is something which is more important question. So image problems, I mean to say object detection problems. I think nowadays it is much faster, right? Now even Retina Net, I think 1, 2, 3 weeks back, you don't even need this bounding box and classification. Or it's now a transformer driven object detection model that that got released. Correct. So it is. I mean, the models are evolving in a beautiful manner. Maybe I would probably share another blog post where there is another very new model which came into picture. I think it is YOLO 5 or RetinaNet. Which one to use? So YOLO 4. I think YOLO 5 is not yet released. YOLO 4 is something which is released in April. Okay, YOLO 4. See, YOLO 4 and RetinaNet is something which is, you see, if you want very fast performance, YOLO 4 will help you. If you want RetinaNet, if you want to have performance and accuracy, RetinaNet will help you. So it depends on the problem, but you have to fine tune. You have to try different models. You have to try YOLO. You have to try RetinaNet. But in my what I felt is RetinaNet will solve your problem. RetinaNet is faster. You could see the result, that is it is very faster, right? So YOLO also is faster, but I doubt on its performance. But now YOLO 4, I think it also performs better. Yeah. Any other questions? Okay. Anything else? I'm ready to take up. I mean, even if it extends some time, yes. Okay. I think that's it. All good now. Okay. Thank you, everybody. Thanks, Vishal, for coordinating, for your patience. I should thank you very much. Thank you so much. Thanks, Vishal. Thank you. And I'll have another presentation on Azure Machine Learning Service also, which is going to happen on June 29th. So please attend that also. I mean, you will know how to build a model in Azure Machine Learning Service and how to deploy it. All those things I'll be showcasing in that meetup. Okay. Thanks for everybody. Thank you. Thanks Vishal. Thanks everybody who has attended the meetup. Thank you. Okay.